All right. Good afternoon, everybody. Welcome to this lecture. Before we start, let me briefly give an introduction about Professor ELLIS. Professor ELLIS received his PhD from the University of Cambridge in 1971. And after a short period of postdoc position at SLAC and Caltech, he settled at CERN and hold a permanent position since 1978. He has been the head of theory division at CERN for 6 years. And Professor ELLIS was elected as a fellow of Royal Society of London in 1985 and a fellow of the Institute for Physics in 1991. And currently, he holds the position of the Clerk Maxwell Professorship in King's College, London. Professor ELLIS' research mainly focuses on phenomenology of particle physics and its interplay with astronomy and cosmology. So far, he has authored about 1,000 papers. And one proposal he made in 1973 has led to the discovery of gluon in 1979. We know gluon is a force carrier of strong interaction. And he has also pioneered the study about how to produce and discover Higgs bosons at colliders. And next, let's welcome Professor ELLIS to deliver the lecture. Okay.
Okay, so thank you very much for the kind introduction, and thanks again for the invitation to come here for this very interesting conference. So my topic today is a little bit different from the actual talks in the conference, but I think you're going to see that there's significant overlap. It concerns another aspect of fundamental physics and cosmology. And of course, all of fundamental physics is connected in some way. And there's connections at the theoretical level, there's connections at the experimental level. And I would argue that actually, at least briefly in the course of my talk, that gravitational waves might actually be responsible for our existence. But I'll come back to that later on. And I know there are at least some people in the audience who are interested in gravitational waves. For example, Tao himself is interested in gravitational waves. And we'll be hearing later on in this conference how accelerator technologies might actually be useful for detecting gravitational waves in the future. So I'm going to be talking about various different aspects of gravitational waves. So I'll start off by reminding you of the history of the discovery of gravitational waves, first indirectly through observations of the binary pulsar, and then subsequently, of course, starting in 2016, with the discovery of gravitational waves emitted by black hole binary systems. In addition to gravitational waves from black hole binaries, there have also been observations of gravitational waves from binaries involving neutron stars, which I find intriguing, and I'll mention why a little bit later on. Now, of course, we know that there are present in the centers of most galaxies supermassive black holes. And I think that the hunt is now on for gravitational waves produced by those supermassive black holes, either supermassive black hole binaries or other objects being absorbed by those supermassive black holes. But the question in my mind, though, is how did those supermassive black holes get formed in the first place? And surely there must be intermediate mass black holes between the LIGO-Virgo ones and the active galactic nuclei. And one of my research interests is trying to think about how one could actually find direct evidence for those. And I'm involved in a project in the UK called AEON, which proposes to use atom interferometry as a novel technique to look for gravitational waves in a frequency range intermediate between LIGO-Virgo and the LISA experiment. So as you're probably aware, last year, middle of last year, there was a lot of excitement generated when several experiments measuring emissions from pulsars observed small irregularities which are attributed to gravitational waves, but gravitational waves in a very different frequency range from those observed by LIGO and Virgo, in the nanohertz range. And there's a lot of discussion taking place now amongst astrophysicists as to what emits those gravitational waves. Of course, the astrophysicists would like to think that they come from binary systems of supermassive black holes. But it's possible that those nanohertz gravitational waves might be emitted by some fundamental physics process coming perhaps from the very early universe. And in fact, I'm going to argue towards the end of my talk that those physics beyond the standard model scenarios actually fit the data better than the boring astrophysical interpretation in terms of mergers of supermassive black holes. Okay, so we all know that Einstein predicted the existence of gravitational waves back in 1916. What is perhaps a little bit less well known is that 20 years later, in 1936, he wrote a paper trying to retract the prediction. And he sent it off to a journal, and the journal sent it off to a referee. And Herr Einstein was deeply insulted that one of my papers be sent to a referee. But the referee wrote a report saying, well, actually, Professor Einstein, I think that you got it right the first time, and the second time, the paper's not quite right. So Einstein withdrew the paper, rewrote it, sent it to another journal, and continued to predict the existence of gravitational waves. So the first indirect evidence for gravitational waves came from observations of the binary pulsar discovered in 1974 by Hulse and Taylor. So the same year as charm was discovered, gravitational waves were at least indirectly discovered. And for decades subsequently, the changes in the orbital parameters of this binary system have been measured, and they agree extremely well with the predictions of Einstein's theory of gravitational waves. It's not actually the most precise measurement of gravitational waves. There's an even more precise binary pulsar system where the predictions of Einstein are verified at a level of something like 1 part in 10 to the 5. Okay, so then we fast forward to 2016 and the direct discovery of gravitational waves by the LIGO and Virgo experiments. So you've probably seen these pictures before, but it's always nice to see them again. So these are the two detectors of the LIGO experiment in the state of Washington and the state of Louisiana. And as you know, also in Europe, there is the Virgo detector, very similar to one of the two LIGO detectors. So the basic principle of these is laser interferometry. So you start off with a laser beam, you split it. The two parts of the beam follow different trajectories. When they come back together, they interfere, and the interference pattern depends on the passage of a gravitational wave. Or in the case of the Louisiana detector, the passage of an alligator. So these detectors observed an event towards the end of 2015, which they analyzed and published early in 2016, which was the first direct observation of gravitational waves, which you see here. So these are actually the traces from the two LIGO detectors. So you see sort of a signal which seems to blow up and then decay away again. And in the bottom two panels, you can perhaps just about make out a line which is the fit of a gravitational wave template to those data. And they agree very well. The residuals are very small. This is undoubtedly the observation of gravitational wave train passing through the two LIGO detectors. So here you see the features of that gravitational wave train. So early on, when the two objects in the binary system are relatively far apart, they evolve relatively slowly, the so-called in-spiral phase. And that's the phase in which the binary pulsar, which I mentioned earlier on, is in at the moment. So the orbital parameters are changing very slowly. It's estimated that that binary neutron star will finally merge in something like 100 million years' time. So in the sort of black hole system that LIGO and Virgo observe, the process goes much quicker. The objects get closer together, the frequency goes up, and then you get to the actual merger where the two black holes actually come into contact, and then there's a ring down as the sort of dumbbell object made by these two objects in contact relaxes to become, again, an essentially spherical black hole. So just to situate you, the black holes are gradually accelerating up until the merger and eventually reach something like half the velocity of light. So we're very proud of the Large Hadron Collider, but it pales in significance compared to the sort of astrophysical colliders which are taking place all around us. So as you see, as the separation goes down, the velocity goes up, until eventually you have a sort of final paroxysm. So the first binary system to be observed directly was this one here, consisting of two black holes weighing of the order of 30 solar masses each. And one of the most striking features of this was the amount of energy which was emitted in the form of gravitational waves. It's equivalent to something like 3 solar masses. And that's one of the reasons why I had this sort of line in my title talking about the biggest bangs since the Big Bang. The amount of energy which is released in these events is much larger than, for example, a supernova. So this is another representation of what LIGO saw in that first event. And you can see that as a function of time, the frequency of the gravitational waves goes up, what's called in the business a chirp. To those of you who are perhaps not native English speakers, maybe you don't know what a chirp is. A chirp is the noise made by a bird, and I'll try to imitate it. It's a chirp. So the fact that this frequency changed precisely as predicted by Einstein's theory can be used to check his theory. For example, as LIGO pointed out, it gives you a constraint on the mass of the graviton, which is something like 10⁻27 of the mass of the electron. And it also tells you that waves of different frequencies travel with approximately the same speed. So that constrains the somewhat outlandish possibility of a Lorentz violation in the propagation of gravitational waves. Okay, so that was 2016. So since then, dozens of black hole binary systems have been observed, and this is a rather nice sort of picture showing the masses of merging black holes, shown as these little blue disks, and then there's an arrow pointing to the final merged black hole. So the merging black holes have masses ranging from a few solar masses all the way up to something like 80 solar masses. Which of course begs the question, what happens when you go to larger masses? Are there heavier black holes? Well, of course we know they're heavier black holes because they're the supermassive black holes in the centers of galaxies. But it's an open question whether there are black holes weighing, let's say, between 100 and 10 to the 5th or 10 to the 6th solar masses. Astrophysically, one expects a gap in the mass spectrum, but that has not yet been identified, but one certainly expects heavier black holes to exist, and those have also not been directly identified. So you also see here some sort of red or orange dots, and those are neutron stars, typically weighing between 1 and 2 solar masses, which, when they merge, may produce a low-mass black hole.
What is the horizontal scale? Sorry.
Arbitrary. It's just to make a pretty picture. So the first binary neutron star system to be observed to merge was seen in 2017, and that also created a lot of interest amongst astrophysicists as well as particle physicists. Because in addition to the gravitational wave signal, which you see down here, there were also observations across the electromagnetic spectrum. And for example, Fermi and Integral observed a flash of light which occurred just after the merger took place, and that tells you that the velocity of gravitational waves is very similar to that of the velocity of light, differing by maximum something like 1 part in 10 to the 17. And then there were many follow-up observations by something like 70 different astronomical groups which observed electromagnetic radiation in various different frequency ranges. So let me just mention one of those observations. So this is an observation of a particular excitation level in tellurium. And you can see there's a nice little tellurium peak various times after the original merger. They also looked for peaks corresponding to other elements, but this is the only one which is clearly identified. So why do I pick this one out? Well, according to calculations of nuclear synthesis, there are several different processes by which nuclear synthesis occurs inside stellar objects. And one of them is something called the R process, where you've got a neutron-rich environment and a nucleus can absorb many neutrons before it has time to decay. And that R process mechanism is expected to produce tellurium. So this observation is very much in agreement with that idea of nuclear synthesis in the mergers of neutron stars. Adjacent to tellurium in the periodic table is iodine. And according to the calculations, iodine should be produced at almost exactly the same rate as tellurium. And the reason why I emphasize this is because iodine is essential for human life. Remember your thyroid? Your thyroid uses iodine. Where did that iodine come from? Well, very likely from mergers of neutron stars. And what enabled those neutron stars to collide? Gravitational waves. So that's why I claim that very possibly our existence we owe to gravitational waves, which I think is a remarkable connection. Okay, so
abundance curve. How does this abundance curve compare with the reality?
we compare with.
With the experimental data.
So it compares pretty well. So there's lots of peaks and dips, but those agree really remarkably well with, for example, the solar system abundances for those different heavy elements. Now, one expects that in addition to the R process, other stellar processes also contribute to the production of heavy elements, but most of them come from the R process. And if you're interested afterwards, I could show you a comparison between the two. Okay, so I've talked about mergers of stellar mass black holes and binaries. But we expect a lot of other interesting things to be happening in the spectrum of gravitational waves. And this is a plot which is maybe a bit too confusing, but it talks about the various different possibilities. So there could be gravitational waves emitted by supernovae, or by compact objects captured by supermassive black holes, by binary systems of supermassive black holes. There could be polarization in the cosmic microwave background radiation induced by quantum gravitational effects in the very early universe. So, there's a lot of astrophysics out there. There's a lot of cosmology out there, and potentially also a lot of new physics. So far, the observations have been with laser interferometers, LIGO Virgo, and coming up there's the LISA experiment. I'll talk about that more in just a moment, which is a laser interferometer in space. But there are other techniques which can be used to look for gravitational waves. So one of them is looking at the timing of pulsars, so-called pulsar timing arrays. And these are what announced in the middle of last year the apparent detection of gravitational waves in the nanohertz range. And I'll come back to that detection and its possible interpretation later on. Now, I should declare a personal interest. I'm interested in using atom interferometers to look at gravitational waves in a frequency range in between LIGO Virgo and LISA. And I'll discuss that in a moment. And there's also the possibility that there might be very high frequency gravitational waves, which might also be indicative of new physics. And there's a talk towards the end of the conference which is going to discuss possible applications of accelerated technology to searches for them. Okay. Supermassive black holes in the centers of galaxies. So this is the famous picture of light coming from around the black hole in the center of the M87 galaxy, which has a mass of about 6.5 billion solar masses. So the LISA project is to put laser interferometers in space with the idea of measuring gravitational waves emitted by processes involving those supermassive black holes. So it can look for objects being eaten by supermassive black holes. It can look for binary systems consisting of supermassive black holes. And with a bit of luck, it might also be able to detect mergers of those supermassive black holes. So there's a question mark here concerning intermediate masses. The point here is that binaries consisting of, let's say, 10 to the 4 solar mass objects would emit gravitational waves in a frequency range intermediate between LIGO, Virgo, and LISA. And as I mentioned, one of my interests is to try to look for such intermediate mass black holes using atom interferometer. So here is a cartoon discussing possible ways in which you might make supermassive black holes. So there's what I call the Lego brick model, where you postulate the existence of an early population of black holes weighing maybe 100, perhaps 1,000 solar masses formed by the collapses of a first generation of stars, called confusing by astronomers population 3, but they're actually the first. And so you might stick those little Lego bricks together and you put enough of them together in some sort of hierarchical process, and eventually you might get to a supermassive black hole. Then another possibility is what I call the Duplo model. So I don't know how many people have kids here who play with Lego or have played with Lego. Yeah, a bunch of hands go up. So you know there's tiny little Lego bricks, and then there's intermediate-sized Lego bricks, and those are the Duplo bricks. So the Duplo bricks, those would come from black holes in so-called proto-galaxies. Maybe they weigh 10 to the 4, 10 to the 5 solar masses, and maybe if they merge, then that's a sort of a quicker way to get to supermassive black holes. Or it could be that those proto-galaxies merge before making black holes, and then you go straight to a supermassive black hole. So this is sort of a cartoon illustrating the various different possibilities. But all of these possibilities suggest that at some point in the history of the merger tree, there have been intermediate mass black holes, some of which may have got left over, and they may still be in the universe today, still trying to merge and still emitting gravitational waves. Okay, so here's the frequency spectrum, gravitational waves. Here's a range around 100 hertz, where LIGO and Virgo have been making their discoveries. Here's a range around 10 to the minus 2, 10 to the minus 4 hertz, where LISA will be observing. Here's the range around 10 to the minus 8, 10 to the minus 9 hertz, where pulsar timing arrays are now seeing gravitational waves. And there's a gap here between LIGO, Virgo, and LISA. And it's also worth mentioning that there's a gap here also between LISA and the pulsar timing arrays, but I won't be discussing that so much in this talk. So in this frequency range here, you might be able to see processes involving those hypothetical intermediate mass black holes. And in either of these gaps, you might see phenomena associated, for example, with phase transitions in the early universe or cosmic strings. I'll come back to those possibilities later on. Okay, so how do we access that gap? So one possibility is with atom interferometry. And this plot here shows you the sensitivity of various different detectors, either actual or planned or potential. So you see here the high sensitivity of LIGO et al. around 100 Hertz. You see laser optimized around 10 to the minus 2, 10 to the minus 3 Hertz. And then in this gap in between, that's where we claim that atom interferometers could play a role. And what you see here is, okay, so LIGO Virgo is optimal for objects weighing, let's say, a total of 60 solar mass. But if you want to see the early in-spiral stages of such mergers, then you want to look in that intermediate frequency range, for example, with an atom interferometer. The atom interferometer would be ideal for observing the final stages of mergers of intermediate mass black holes weighing 10 to the 4 solar masses, and the in-spiral stages of those mergers could be observed by laser. So you see this sort of complementarity and synergy between the different detectors. And in order to really understand the way in which black hole ecology works, you want to have coverage over a full range of frequencies. So what is an atom interferometer? Well, it's basically the same thing as a laser interferometer in principle. So for a laser interferometer, you have a beam splitter, and you've got two sub-beams which follow different trajectories. They then come together again, they interfere, and you look for the way that an interference pattern is affected when the gravitational wave passes by. So with an atom interferometer, you start off with a cloud of atoms. You hit them with a laser, which splits them into two subclouds. The laser excites a half of the atoms. When it excites them, it also imparts momentum, and so they move away from the ground state atoms. Then you hit the two clouds again, and you can do it in such a way that you bring the two subclouds back together again, and then you can interfere the two subclouds, and when you do that, that is sensitive to things like the passage of a gravitational wave. So that's the basic principle. So this is what is illustrated here. You've got two clouds of atoms in the ground state and the excited state. Gravitational wave passes by, and you get an extra term in the interference pattern, and just basically the same principle, as I said, as a laser interferometer. So as I mentioned, one of my personal research interests is as a member of the AEON collaboration, which is a project to build a succession of atom interferometers centered in the UK, although we work closely with the MAGIS collaboration in the US, and there are also other atom interferometer projects in France and China, also Germany. So we're still in the early stages, and we envision a series of detectors starting off at a sort of typically 10-meter scale, 100-meter scale, kilometer scale, and then hopefully eventually going into space. So the 10-meter device we're now ready to construct in the UK in the basement of the Oxford Physics Department. For the 100-meter device, there's a couple of possible sites. One of them is at a mine in the northeast of England, and another one is at CERN in one of the LHC access shafts. So we see interference patterns. Of course, we're nowhere near the sensitivity you need to start detecting gravitational waves. That's a long way into the future, but at least the basic principle has been demonstrated. This is how the 10-meter device would fit into the basement of the Oxford Physics Department. So this is a modern building, seismologically very stable. It's got a nice space for a laser lab at the bottom here, vertical height a bit over 10 meters, and design is being complete for this detector, and we're now waiting for the final tranche of funding so that we can actually go ahead and build the thing. So this is how you could put a 100-meter device at CERN. So here is the LHC, about 100 meters underground, a whole bunch of access shafts. The one that looks most suitable for what we want to do is actually at point 4, where the LHC accelerating cavities are located. And it's got a nice big cross-section. It's 140 meters. It's ideal for our purposes. So if we can demonstrate that we can build and operate successfully the 10-meter device, then we may be knocking on CERN's door for a 100-meter device. So I advertised atom interferometers as being sensitive in a range of frequencies intermediate between LIGO, Virgo, and CAGRA, and LISA. And that's illustrated here. So, so here we have the sensitivity of LIGO, the sensitivity of the Einstein telescope proposed in Europe, sensitivity of LISA, and slotting in between is AON, and that slotting in between gives you the complementarity and the synergies that I was talking about earlier on. And this is a corresponding picture, but this time with a space-based atom interferometer called EDGE. So notice the horizontal axis here. So the atom interferometers are typically sensitive around 10 to the 3, 10 to the 4 solar masses, just in that intermediate mass black hole range. Okay. So now let me come on to pulsar timing arrays. So what these do is that they look for the arrival times of pulses emitted by pulsars. Now, the emission by the pulsars is extremely regular, but in propagating through space-time to each Earth, the arrival time can be modified by the passage of a gravitational wave. Now, if you're just looking at one pulsar, you can't be sure that what you're seeing is not some noise in the dynamics of the pulsar itself. So what you do is you look for dozens of pulsars, and you try to look for some sort of coherent noise pattern, coherent between the different pulsars. So already, was it 3 years ago, one of the pulsar timing array experiments called Nanograv reported seeing apparently some sort of common noise, but then last year 4 collaborations simultaneously announced the observation of a common noise process, and they also reported characteristic feature of gravitational waves. That the first observations, they couldn't tell you what was the source of the common noise, but now it certainly looks like gravitational waves. So this is a summary of the data reported by the Nanograv collaboration. So this is a North American pulsar timing array. They actually have the largest data sample, and I think their data provide the strongest evidence. So what you see over on the left here is correlated time delays between the various different pulsars, which an effect which seems to grow as you go down to low frequencies. So the characteristic frequencies here is 10 to the minus 8, 10 to the minus 9 hertz, and that's why they're called nanohertz, and that's why it's called nanograv. And in the lower left picture, you see various fits to the spectral shape as a function of frequency, and we'll come back to that later on. So on the right-hand side, you see the angular correlation between the apparent noise signals in pulsars in different directions. And as you might imagine, but I'm not going to go through the maths, got a gravitational wave, effectively it has spin 2, it's going to give you some characteristic angular dependence of that correlation. And that was first pointed out by Hellings and Downs, and their prediction is in excellent agreement with the observations by Nanograv, and Nanograv claims very strong evidence at the level of something like 4 sigma to have observed this Hellings-Downs angular correlation. So as I mentioned, there's a total of 4 pulsar timing arrays that have presented results. There's a collaboration between the European and Indian pulsar timing arrays. There's a pulsar timing array group based in Australia, the Parkes pulsar timing array. And there is also a Chinese pulsar timing array, which is basically using the FAST radio telescope, which is located not so far away. So the Chinese PTA present their data in a different way, so I'm not going to make a direct comparison between their data and the other pulsar timing arrays. But you see here that the other pulsar timing arrays report a very consistent set of observations. They all see this spectrum of noise going up at low frequencies, and they all see a spectral index, which is roughly compatible between the different experiments. Now, there's one thing which I didn't mention, and perhaps I should have done. So, some 20 years ago, an astrophysicist called Sterling Finney started thinking about what that spectral index should be. And he did a calculation based on a model of supermassive black hole binaries on their way to merger. And he made a prediction that this spectral index should be 4 1/3. That's that dashed line here. Now that dashed line is, okay, it's not in perfect agreement with the data. The data seem to want a somewhat different spectral index. And that you also see here. Here is the combination of all the data. And again, they seem to be wanting a spectral index which is a little bit different from the prediction from supermassive black hole binaries. And I'll come back to that in a moment. Okay, so if we are looking at mergers of supermassive black holes, we really are talking about the biggest bangs since the Big Bang. If you merge 2 objects weighing billions of solar masses, then you radiate maybe 1 billion solar masses of energy in the form of gravitational waves. You're talking about a mass equivalent to a significant fraction of a galaxy, right? So, Big Bang. So the process by which this occurs is obviously quite complicated because these black holes are presumably sitting inside galactic halos. There's all sorts of crud rotating around the black holes. There's gas, there's dust, there's stars, and the dynamics of those additional features could affect the gravitational wave spectrum. So the beginning of last year, we started hearing rumors that maybe there was going to be some interesting announcement by the pulsar timing arrays, and so we started thinking about how to model this process of the mergers of galaxies with supermassive black holes and what the spectrum of gravitational waves might look like. So I'm not going to go through the details of that, but we use all standard astrophysical models for how many black holes you find in halos of what mass, and what magnitude, and so on. And then we had a little arbitrary factor at the end, which is the probability that once you've got these two galaxies merging, what's the probability that their black holes will actually merge in an observable way. So our model fitted the available PTA data quite nicely. And in our model, you could predict the rates of mergers, not just of the supermassive black holes that would be responsible for the PTA data, but also the masses of smaller mass black holes that you could potentially observe with other detectors. So according to our model, indeed, the pulsar timing arrays are seeing mergers of supermassive black holes. There would also be mergers of somewhat smaller black holes, which LISA could observe, and intermediate mass black holes, which could be observed by atom interferometers. So according to our model, there's something for everybody. Yes, the pulsar timing arrays could be seeing supermassive black holes, but smaller mass black holes could be observed merging by other detectors. Now, there is a small problem. So you remember that I commented earlier on that Finney, back in, 20 years ago, had predicted a specific spectral index for the emission of gravitational waves. And it doesn't agree perfectly with the data. So is there some phenomenological fix? Well, the phenomenological fix is to remember that these black holes are merging in a complicated environment, and there could be modification of the merger through interaction with the environment. The merger is not taking place in isolation. So there's various different models for how that interaction with the environment might occur, and we just took a very simple phenomenological approach and tried to see what the data wanted in terms of possible environmental effects. So this is a picture taken from a paper written in 2016, where you see some of these various different mechanisms and how they might operate at various different separations of the black hole binaries. So there's dynamical friction. There's what's called loss cone scattering, where the black hole loses energy to stars, which it sort of flings out. Then there's a viscous drag, and eventually there's also gravitational waves. So there are a number of different mechanisms whereby environmental effects might affect the evolution of the binary system. Which of these effects might be the most important for the interpretation of the PTA data? We don't know. We just take a phenomenological approach and ask, is there evidence in the data that there should be an environmental effect? And the answer is yes. So the scenario in which the binaries evolve purely by the emission of gravitational waves is illustrated here by the blue, what are called these blue things are called violins. So what these blue things represent is the probability density for the energy emitted in a given frequency band, okay? And so the probability density has a sort of shape like this. So you turn that on its side, and you've got this violin shape. Is that clear? Maybe. Okay. So anyway, so the blue violins are the prediction if these systems evolve purely by the emission of gravitational waves. And the orange violins are the data observed by nanograph. And, it doesn't agree so very well. On the other hand, if you switch on environmental effects, then you can get a better fit to the data. And the improvement in the fit is significant, but not, you can't claim discovery of environmental effects on the basis here. It's something like 2-3 sigma, something like that. But a better fit to the PTA data is given if you have environmental effects on the evolution of the binary systems. Okay, so that's astrophysics. And you're probably saying, well, just a moment, how about some particle physics? What's the connection with what we do? Right. So you can ask yourself the question, what alternative sources are there for the gravitational waves being observed by the pulsar timing arrays? And there's various different scenarios that have been postulated, invoking fundamental physics, cosmology, and scenarios beyond the standard model. And so we and others have set out to analyze them, and let me just show you some of the results. So one possibility is that through space there is a network of cosmic strings. So there's all sorts of unified scenarios in which cosmic strings exist. As the universe expands, those strings move around, they sort of meet each other, and they form loops, possibly. And those loops then emit gravitational waves, and they contract, and that gives you a cosmological background of gravitational waves. So the precise strength of this signal depends on the probability that when two strings pass through each other, they actually make a loop. And that depends on your string model. The simplest possible string model, you always get loops, but there are other string models where you don't. So here is a comparison that we did. On the horizontal axis, there's the string tension. And so we find fits where the string tension is, so G here is Newton constant. So this would be a string tension sort of in some sort of grand unified energy scale. And these constraints here come from LIGO, Virgo, and Cagra. So this is the current constraint. And this is where they expect to get with a few more years of operation. And they actually exclude a significant fraction of this cosmic string scenario parameter space. And in a few years' time, they may be able to explore almost all of this cosmic string scenario. But for the moment, the cosmic string scenario works, and actually it gives you a better fit to the data than the astrophysical model. Even the astrophysical model with this phenomenological tweak of environmental effects. So that was one scenario. So another possibility is that early in the history of the universe, there was some sort of a cosmological phase transition, which is typically thought to proceed by the formation of bubbles. Those bubbles generate gravitational waves, they collide, they create turbulence in the plasma, which generates more gravitational waves. So we also compared that scenario with the data, and there's a chunk of that model's parameter space which is also excluded, but there is a region which is allowed. And interestingly, it would correspond to a scenario where the dynamical scale of these bubbles is around a GeV, or possibly even less. Now, in the standard model, that doesn't happen. So you can say, well, there's a QCD phase transition. Yes, with a QCD phase transition, it's expected to be smooth. It's not expected to produce bubbles. So it's not going to produce gravitational waves. But maybe in the hidden sector, at a scale around a GeV, you could generate this sort of bubbles. Another scenario is that you might have domain walls. So supposing you have some scenario with a Z2 symmetry, and then you're going to get a wall between the different regions of space, and that model can also be made to fit the data. But again, you would require some dynamics at the GeV scale, presumably not in the visible sector, but maybe in the hidden sector. So we looked at a whole bunch of other scenarios based on particle physics beyond the standard model and cosmology. I'm not going to go through them all. Anyway, here's a comparison of those models with the nanograv violins. And all of these models fit the data pretty well. In fact, all of these beyond the standard model scenarios fit the data better than astrophysics. Now, I'm not saying that the pulsar timing array data are evidence for physics beyond the standard model. I'd be crazy to do that. But watch this space. So how do you discriminate between these different scenarios? Well, many of these scenarios actually wouldn't predict anything observable in higher frequency experiments. Cosmic strings would. They would predict a very smooth spectrum extending all the way up to higher frequencies. The astrophysical merger scenario would predict the observability of mergers of lower mass black holes. And both the cosmic string and the black hole merger scenario would predict things that could be seen in this intermediate frequency band in between LIGO, Virgo, Cagra, and LISA. So that brings me to the end of my talk. What's the interpretation of the nanograv data? I don't know. Could be astrophysics, but it could be fundamental physics. It could be that what is being observed by the pulsar timing arrays are just the biggest bangs since the Big Bang. Very boring. Or it could be that they're observing physics beyond the standard model. So as I argued, supermassive black hole binaries are disfavored, even if you put in environmental effects. Cosmological BSM scenarios fit the data better. Atom interferometers could help you distinguish between the different models, and time and more data will tell us what is the interpretation of nanograv and more about the full spectrum of gravitational waves. Thank you.
Okay, thank you, John. Very nice overview. Next, let's invite questions from audience. Michelangelo.
Thank you, John. That was very nice. My question is the following. If we take mergers, the signal has a lot of features, the intensity, the frequency, and out of those one can learn the respective mass of the two objects, indications about the spin, and so forth and so on. So what are the features of an nanograph signal that allow to go beyond and maybe even perhaps separate these different models? Is there anything in that signal that could be used?
I don't think so. I mean, this is so. This is a stochastic signal which is generated by a population. Now, if we're lucky, at some point in the future, we might be able to see individual binaries superposed on that background. So if I, okay. So if you look at this plot here, you see, for example, there's this bin. So there's one particular frequency where the signal seems to be stronger than in the other bins. Now, it could be that that is due to a statistical fluctuation in the population of nearby binaries. And if that's confirmed with future data, then one might be able to tell something about that particular binary system. And indeed, the sort of thing that you were describing, that you were asking about, like, for example, the spins of the black holes, like the direction. Okay. So you can also hope to measure the polarization. That tells you whether the system is facing you or whether it's orthogonal to you. So that sort of game you should be able to play in the future, but I think at the moment you can't do that. Well, I might mention there's another feature which you can look for. So these things merge, and then following that, the sort of dumbbell relaxes to a ball, roughly speaking. And so you can hope to look for higher order modes during the ring down. And there's some evidence of that from LIGO, Virgo, but nothing definitive. And that I think is something which is on the list, in the future for observations at lower frequencies also.
Okay, sure.
How was the upper bound of the gravitational mass was estimated? You mentioned this.
Okay. So remember the Klein-Gordon equation, right? So p squared equals m squared, roughly speaking. So e squared minus momentum squared is equal to m squared. So as you vary the frequency, which shows up as E, okay, then you can become sensitive to the m in the Klein-Gordon equation. So to take the extreme limit, if you go to a frequency which is less than the, if you like, the rest mass frequency of the graviton, then there's...
It's the kinetic mass
right.
which you are talking about.
No.
It's the moving mass which you are mentioning. It's not the rest mass which you are talking about.
No, I'm talking about the rest mass.
The rest mass.
Yeah, the rest
So
mass.
if it's 10 to the minus 26 electron mass,
Right.
and then that will gives you the distance of the gravitational interaction. But that will be very short.
Okay, so there's other constraints on the graviton mass, and I'm not necessarily saying that this is the best limit, but it's an interesting limit, right, which just basically comes from the velocity of the gravitational wave.
I noticed that at the frequencies that we can observe that all the different phenomena are frustratingly similar and then they diverge once we go into frequencies we can't observe. Is there any physical reason why the different phenomena sort of bunch up at these frequencies and then diverge once you get to other frequencies?
Well, I think the basic reason for that is that the nanograv data are not perfectly described by a single power law frequency dependence. You need a little bit of curvature. So if you construct a model which gives you a bit of curvature, then maybe if you go a bit further, it's going to curve down. I think that's basically what's happening here.
We have questions from that side.
Hi, I have a question about intermediate mass super like black holes you mentioned. Like, for what reason we shouldn't expect like we should first see them in X-ray or other electromagnetic window rather than gravitational wave?
So there are indications of a population of intermediate mass black holes coming precisely from electromagnetic observations. So somewhere in my computer I have a plot which shows you, what claims there are. I would regard them as not being completely established, but probably they're right. Okay, but I think it would be interesting to observe those intermediate mass black holes in gravitational as well as electromagnetic spectrum and correlate the two. For example, do you get flashes of light when you merge intermediate mass black holes? That would tell you something about the environment in which the event takes place.
Thank you.
Okay, Manch.
Yeah, thank you, John. So compared to the laser interferometer, that the atom interferometer is more sensitive to the lower frequency, even if their scales are comparable, right? Is it because of atoms traveling at a speed much slower than the light?
So basically, the frequency dependence of the sensitivity is completely different because of the mass of the atom. They're non-relativistic objects as opposed to relativistic.
Yes. So it's because they travel much slower. And there is a factor, basically, it's the speed of light divided by the speed of the atom.
Well, there's a whole bunch of other factors that come in.
Okay.
Okay. But the dynamics is completely different.
Mm-hmm. And could you comment also on the, technology readiness for the atom interferometer? Is it challenging or?
Okay. So I would say that the world leaders in this are a group at Stanford that have built a 10-meter vertical interferometer, which they've actually used to measure the gravitational analog of the Aharonov-Bohm effect and to check the principle of equivalence. But they use a different species of atom from what we would propose to use. It's not suitable for detecting gravitational waves. Now, another team at Stanford is building another 10-meter device, which is based on the same strontium atoms as we propose to use. But that's still under construction. But I would say that the Stanford people are the world leaders. Now, there's a project in the US, which I mentioned, MAGIS, which would extend that technology to a 100-meter device, which would be located in a vertical shaft going down to the MINOS neutrino beam. And so they've now basically got all the funding they need to build that device. I don't know how long it's going to take them to actually do it. But like I said, I think they're the world leaders. Now, I would mention also a team in Germany, in Hanover, that is also building a 10-meter vertical device, again using a different atom, but they, I think, are the most advanced in Europe. There's also a French team which has got funding to build a 100-meter device, but a different sort of geometry. I guess I should have explained. Our geometry is basically that we throw the atoms up vertically and then they fall down, but the rate at which they go up and fall down depends on whether they're in the excited state or not. Okay. So the French are using a horizontal geometry. And then in China, there's a group in Wuhan which is doing both. Right? So they've got a vertical shaft, they're digging horizontal galleries, and I'm not sure how advanced they are with actually doing experiments, but they've certainly got a very ambitious project.
Yeah, thank you.
Hi, Jia, please.
So, okay, thank you for the very interesting talk. So several years before, we invited Oide-san to give a talk on the gravitation wave measurement by circular colliders machines like FCC or CPC. So these circular machine, the frequency range of this gravitational wave, I forgot. It's lower or higher for the moment. I forgot. So, do you work with him on this subject? I mean, discussed with him how you comment on the possibility of this huge machine on the gravitation detection.
So we actually had a workshop at CERN in which he participated a couple of years ago, and I'm afraid the conclusion of that was that accelerators are not interesting devices for measuring gravitational waves. There are several ideas that were proposed. Uede-san, also Pisin Chen from Taiwan, also presented his ideas. I don't think they're competitive, which is not to say that there isn't an interface between gravitational wave experiments and accelerator physics, because, as will be discussed in the talk later on in this meeting, the sorts of superconducting RF cavities which you guys have been developing could be interesting detectors of gravitational waves at high frequencies. So this is something maybe to watch for the future.
Okay, thank you.
A question over there, yeah.
Hi, I'm also interested in the atom interferometry. That following Manchi's question, that so right now, if it works for 10 meters, 100 meters, it fills in the gap between LISA and the ground-based gravitational detectors. But if you send it to space, would it fill in the gap between the pulsar array and the LISA for the gravitational wave frequency?
No. So what it would do would give you higher sensitivity in that intermediate frequency band. So it would give you higher sensitivity in the London gap, not the Hong Kong gap.
Okay, thank you.
Maybe I can find a slide which... Yeah. Okay, so you compare what we call edge over here with aeon over here, okay? And so it's a similar frequency range, but much greater sensitivity.
Yeah, thank you.
Hi, Roger.
Hi, John. So I see you have a very broad bandwidth for the gravitational wave, but what about the high frequency, or is there any limit on the high frequency for our interest?
So this slide here indicates sort of the sorts of sources that people think about, which go up to something like a kilohertz. So there have been some sort of speculations about what there might be at higher frequencies, but I'm going to defer comment on that to the penultimate talk in the conference.
Hi, Nakada-san.
Thank you very much, John. When you show this violin plot, it looks like a more mandolin rather than violin. There's no two shapes. It's only one drop, is it? Or the shape? I was wondering first. It's like more mandolin rather than violin to me, or am I mistaken?
I'm tempted to say that it looks more like a penguin. Sorry.
And in other words, is there any sort of waste, or it's not? The shape.
So the thickness here is basically the
That one, yes.
the probability density function. So the way that we would normally see that is we would turn it through 90 degrees, and we would only show a half of it, and we'd see a bump. Okay. Now, in principle, you could have a probability density function which is bimodal, right? In which case you would get a waist, and so it would look a little bit more like a violin.
What I thought of waist. Yeah, okay. Then simulation in principle or prediction in principle depends on the environment of the particular system. So it's not a unique prediction from one plot, but in principle there's a distribution of predictions, right?
Right.
So at this moment it's not just due to the statistical fluctuation, or not, it's not clear, because there's only basically one event you're comparing, or two events.
Well, I'm not sure that I can tell you exactly how many events we're seeing here. But actually there's quite a number of events. So you actually expect the statistical fluctuations to be strongest at low frequencies. And at high frequencies, you may be a little bit surprised to see features like that. But you're not seeing a single event, right? You're seeing some stochastic superposition of binary systems.
But it's one binary system, isn't it?
Right.
Or many binary systems. So this nanograph observations.
So to answer Mike's question, so nanograph has been operating for 15 years. Okay, FAST has been operating for much less, and of course you're not going to be able to see real nanohertz unless you operate for quite a number of years, right? And so this is one of the reasons why maybe nanograph has the best sensitivity at low frequencies. Right? So I didn't really comment on this plot here. This Venn diagram here shows you that actually the data sets are not independent. And there's a job to be done, which is to sort of disentangle this entanglement between the data sets and do a global analysis treating each pulsar independently. And that's something which the IPTA, the International Pulsar Timing Array, is in the process of doing. But this plot here, or these plots here, are just superpositions of the results of the different PTAs. You shouldn't combine them. It's a compilation.
Is there any other questions? Hi.
Actually, I'm wondering this high sensitivity about 100 hertz. So if I calculate the wavelength about the size of the Earth, so are there any particular reason for this particular value of 100 hertz sensitivity?
Well, that's determined by things like the size of the detector, the noise sources, and so on. So that's a long and complicated discussion. Maybe offline we could look at the sensitivity curve, for example, of LIGO, and you'll be able to see how the various different factors limit the sensitivity at higher frequencies and lower frequencies.
So it's no simple picture.
Right.
Hi, John. I have one question. So can you go to your master plot? Probably the last slide. Or, oh yeah, that one.
What you want? That one?
Yeah, this one.
What do you want? This one.
Oh yeah. Okay. This one. Yeah. So can you say something about the detection of mu hertz gravitational waves? My reading from this plot is somehow it is very important to develop the relevant technology for this frequency range to distinguish these models.
You mean in this gap here?
Yeah.
Yeah, well, this is very difficult. And there are some ideas, like, for example, putting laser reflectors on asteroids and measuring on a scale of, let's say, hundreds of millions of kilometers. Right, so you want a detector which is larger, orders of magnitude larger than LISA, okay? And so there are other ideas as well, but that's the first one.
And the scale of the solar system?
Yeah, you have to go to the scale of the solar system, basically. Or at least some significant fraction, some number of astronomical units. But if you've got an idea...
We can invite ideas from our audience. Okay.
You're an expert on planetary magnetospheres. Maybe you could do something with Jupiter's magnetosphere.
Yeah, hopefully. Okay. Are there any other questions? If there is no more questions, then let's stop here. And let's thank Professor ELLIS again.